So as I said last time, a lot of this is kind of background, so we can get on to the more difficult concepts that you guys are probably wanting to learn eventually anyway. I'm a big believer that you have to understand the basics before you go on to the hard stuff, because you'll make a lot of mistakes if you don't do that. So we went over some material last week, but I'm going to move on with a new material. So something that's really important in statistics is random sampling. So basically that's just randomly selecting a subset of values or a smaller group of values within a larger data set or a larger group. And those are basically, if you can think of randomly pulling names out of a hat, it would be similar. So the idea is all of them have to have a chance of being chosen, and they have to be able to be chosen with equal probability. So that's difficult to do sometimes, particularly with surveys. So when you're looking at survey data in particular, be mindful of that. They try and they do their best to represent the whole population, but especially with phone surveys, that's very difficult to do. Hence, the last presidential election, almost all the polls were wrong. So that is due a lot because they do hardline, less cell phones, they call people. So I had mentioned that last week, but this is why this is important. So always keep that in mind, but the random sampling is there just so we can try to get a representative sample of our entire population. Representative means if there are, say, 20% of our sample is between the incomes of 0 and 30,000, we want to have in our sample about that same amount between $0 and $30,000 of when we look at income. So when we randomly sample and we do it in a large enough number, it usually takes those will match the entire population or the entire group that you're trying to study. So we do that as a check on our analyses. And so we can try to make, as I said, inferences about a much larger group with a sample. For example, the census, they sample some people, a smaller group in between the years, but they only do the big census at the end because trying to get a large group of the population, it's very difficult because you have to come and you have to talk to many people probably who have lives and it's difficult and want to do something else. So we are taking those subsamples, so it's cheaper, easier, but we can still have an idea of what that big group it looks like. So are there any questions about this real quick before I move on? Go ahead. Okay, sorry about that. So that's, say you're sending out a mail survey to people and they get it in their mail and they don't even open it or they just look at it, say, I don't have time for this, and don't answer. So that is the voluntary response bias. People are just, certain people may be more likely to fill out that survey and send it back, and other groups of people may be less likely to do that. A great example, if you look on Amazon.com at the reviews that are on there, there's a lot of usually 1s and 5s because people who are angry get on there and leave reviews, and then people who are really happy with the product get on and leave reviews. There's less in the middle because people are just, it was okay, and they don't feel compelled to do that. So that's a good example of when you would have a voluntary response bias. Are there any other questions about random sampling? That's what I just explained. So it's when people don't send back that survey and they choose not to send it back. They're selecting themselves out of the sample. Oh, so you're not selecting them, that's why self-selecting, it's self-selecting, the individuals are selecting. There's also a type of bias where I choose the wrong people or ones that aren't representative of the population. But random sampling is what solves that particular problem, is me choosing the individuals. So does that make sense?
Usually if it's a bias, it's not really random.
Yes, and then that causes, say you had, you were surveying a subsample of the entire US population. So if you sampled Hispanic individuals at a 50% rate, when in the population it was only, say, a 15%, then you're going to overrepresent them, or if their views are different than individuals of different races. So if you were trying to get an idea of how Hispanics differed from Caucasian individuals, then that would totally bias your results if it didn't match the actual population you were trying to make inferences or conclusions about.
I mean, if you're rounding it, or if
no, when you're running statistical tests. So that's what we're going to learn later. So you have to, that's why today was so difficult to write, because it's a little difficult to teach these concepts without applying them in a statistical test, because that's the eventual goal. But we didn't have enough time to do that today. And there's actually other concepts that we need to cover before we can get to that. So you're probably going to be asking a lot today, like, why? I don't understand what this is used for. I'll try to give information about that as much as I can, but it'll get there eventually. Go ahead.
Possible example, if you're interested in people's water use habits,
Mm-hmm.
you send out a questionnaire.
Yes.
And the person that picks it up and says, "I'm trying this," that's precisely the person you want to know about.
Exactly.
They don't care too much about their water use habits, whereas the person that responds is going to be somebody who cares about that issue.
Yes.
So you need to go and say, "No, you respond."
Yeah, and there's ways to get around that, but it's never going to be perfect. So we try our best, and there are ways that surveyors actually, they'll oversample smaller populations and then correct for it when you actually do the analysis. So that's a whole nother ballgame, and we can even, if you guys are interested, have a survey analysis class, because it's pretty difficult. I've had a lot of problems with that, and I've worked to go over the first type of random sampling. This is the one I use most often. So it's the sample function, and I'm gonna, it has the structure down here, but I'll actually show you once I go over one of the other types. I'll actually show you how it works. And I did for it, I'm going to go over that flipping coin example again, just to remind you and kind of cement that that's why it was important. I did use the sample function for that from last week. So the sample function, you create a vector, or similar to just a range of values. In the case of flipping a coin, it was heads or tails. So those are our only two possible options. And I wanted to say sample that heads or tails and choose one of the other randomly 4 times. So that's what this 4 value would be down here. Replace equals true and false. So replace equals false is the default. And again, you can find out what the defaults are by doing the question mark and then the function that you're trying to learn about. So the replace equals false means that once a value is picked once, it's taken out of the pool of possible choices. Here we're doing replace equals true because we're putting, say if we choose heads, we're putting heads back into the possible choices. Because if you say we're not replacing and you wanted to flip a coin 10 times, when you only have 2 possibilities, it's going to throw an error. So since we want to look at that pool of possibilities and look at it again and again, and without taking it out, that's when we would use replace equals true. So we're putting the heads back if the heads is chosen. So when you put this particular code in here, and then you just run that code, it'll return something that looks like this. So, and every time you run it, it's probably going to look different because again, it's random sampling and it's going to choose a different values every single time. So when you would use this is if you had a group of specific values that you wanted to sample from. So that's when you would use the sample function. Are there any questions about this? I will go over how it works in a minute. Okay. So the other really useful one is run if. I just used this one last week, actually. So in this case, this is just a different use case. So it depends on what you want. So if you have that run if function and you want to choose a certain number of values between one value and another. So if you have, in this example we're seeing right now, I want to choose 4 values that are between 0 and 10. And I try to, on my PowerPoints, always like put arrows to what individual arguments. One is like 4, for example, is an argument for this function. So I always try to put arrows in what number corresponds to what concept. So hopefully that helps. And you can see the output below it. It's choosing, again, 4 random numbers between 0 and 10, and that's the output. And it'll look different every time you run it. So go ahead.
It doesn't take it out of the feedback. It's put it as a
Well, this one, that's when you would use sample. If you had specific values that you would want to choose from that were already there, that's when you would use this function. This is for a different use case. So one example, the one that I used this week. So I was writing a code for data that I did not have. So I had not been given this data yet. So I was looking at certain target values and I was trying to predict. I'm going to try not to get too much in the background, but I needed to use these target values in my code. That's all you really need to know. But I didn't have them yet. So I made dummy data, I would call. So I knew that the range was usually between 1 and 3 of the values that I was going to get later on. But I randomly sampled between 1 and 3 the number of values that I needed. Now my results didn't make sense, but I can tell if there's an error in my code, debug that code, and then when I have the data, I can plop it right in and everything will run just the same, only the results will make a lot more sense. So I also use it for this class a lot, particularly when I taught at Bayer, because I had to scramble the data or change the data in some way, because even in the same company, certain people weren't allowed to see certain data. So I had to change everything, our results, to then teach this class. So I use it a lot when I'm trying to simulate other data. So that's an example where you would use this one. Any other questions? Okay. Yes, you can. Yes, so every value has the same chance of being picked. Now, if you go out to a certain number of decimal points, the chances of you getting 2 values that are exactly the same is slim to none, but it is possible, yeah. We're going to cover that once we cover normal distribution. So that's one of the things that we're talking about today. So that one's coming.
Also, if you have a choice,
So most of the data that you get is going to already be a sample for the most part. So I very rarely use a whole population of data because it's usually hard to collect. I mean, it happens. So, but if you have the whole population, you would want to use that for the most, because you're going to get values that are much closer. So this is when specifically for the use case when we're trying to use sample data, because when we're looking at this problem, we're trying to estimate the population mean. If you have the population mean, there's no reason to estimate it. So if that helps explain when you would use this versus not. And for instance, and I'm going to show this later, The prescribing rate data, for instance, we looked at prescribing rates at a county level. We're going to be using that data again today, but it had every single county in the United States in that data set. So there was not a sample in that case. However, for instance, there were missing values in the overdose rates because certain counties are too small, so they're not reliable estimates. So that's a sample versus it's not a good sample because they won't be missing at random, but that's an example of a sample. So this code is online. I'm just going to run the top. So we talked about setting our working directory last time. If you need information about that, go onto my website and it shows you how to do it. And hopefully you can do that and follow along. If you have a Mac, it's going to look exactly like this. With a PC, it's just a little different and it has that information online. So the only package we're using this time, and you should have it installed from last time. If not, you'll have to look again on my website to see how to install packages, but library ggplot2 should work now without an error. Just by the way, this is something that I use all the time, so I do want to mention it. You're probably seeing that I'm not highlighting things when I run them and clicking the run button. I mentioned this last week, but I want to reiterate it because it's so much faster. If you are on a line that you want to run, you can, on a Mac, press Command Enter. On a PC, press Control Enter, and it will run the line that you are currently on or the next one below it. So for instance, here, I'm on the ggplot line. So I'm going to press Command Enter. It runs the library function. And then it drops me down automatically to the next line in my code. So then I can run that, and then I can run the next line. And all I have to do is press Command Enter. Sometimes that's, unless you're going to run most of your code or a large chunk, that's usually faster, particularly if you're checking your data and looking at it after you run the code. So we are going to look at this run if function. I'm going to actually create I thought I created a easier coin flip example, but I can do that on the fly here. So this is the one that I showed online. So you're going to see that this is when an example of when you would use the sample function. So if I wanted to sample heads and tails, I would do coin sample. So if you don't know the arguments, as I said, you would put a question mark and sample in there. And in this case, we're using base R. That's one thing that you'll have to look up online if you don't already know. You'll have to Google the function and it'll tell you at the top, I think, right-hand corner what. See the space up there? That means it's in base R, so it's automatically installed. If I wanted to use the dplyr version, the dplyr would be written up here. So you would know what package it was in. So in this case, you see, and this is how I would do it if I didn't know how to use this function. We'll look down here. Okay, X. So what is X? That's my first argument. I would look at either a vector of one or more elements from which to choose or a positive integer. So that's our range of values that we're choosing from. We can get that information. So that will be what I'll put in first. It's the choices up here, which I will run. Choices is our first value. Now we could go down here and say, okay, a positive number, the number of times we want to choose from. Okay, so say I want to choose 8 times. We would put that next. And then you can see that replace equals false is the default down here. If it has a choice already written, that means it's the default. In this case, we want to change that to replace equals true. And you can put T or F. It's the same as true or false. It's just quicker to type. I'm going to stick with true just so that you're not confused. So we run that coin sample. As just a refresher from last week, I assigned that value to a variable. So it assigned it to coin sample. I have to print that value to see what it actually is. So I just will repeat coin sample here and run that. And now I see what values came out of that function. So When you see an assignment there, that means you have to do the extra step of printing it. If we're looking at our range of values, there's a 50% chance that we're going to choose heads and a 50% chance that we're going to pick tails. So if you do that 10 times, it might be 70% heads and 30% tails, or even closer to 9 heads and 1 tail. So, because that's random again. So it's going to look different every time. But if we run it more than what I'm going to go through is how it would look when I when I run heads or tails and choose 1 10 times, and then I'm going to run it 10,000 times. And what you'll see almost certainly is that the 10 times, every time you run it, it's going to give a different value and they're going to be really far apart. Whereas when you run it 10,000 times, that it's going to look more 50-50. Yeah, and when I was creating this, created a gigantic data set to test it, I forgot to close it. So that's why it was taking a minute. I'm going to close this one as well. I'm going to show in a second. It's just I'm having issues with computer, and so I'm explaining while we're waiting for that. So when you run it 10,000 times, the final result is going to be pretty 50-50. So when you look at the 10,000 times altogether, so now I can show it because that's done. So here, and I think it'll make more sense when we run it. So we have this number of flips. We're going to look at 10 this time. Remember, you have to run this entire function in order for it to work or to errors out. So all this is doing is choosing between heads and tails and then returning the result. What percent was heads and what percent was tails. That's all. You don't have to understand the actual code, but I wanted to do an example for you, and this is called a simulation. So I just ran that. It ran it 10 times. It chose a head or a tails. That's what the code did. So I now look, and this is, and you can see in the comments, I always explain what I'm doing. This will return the percentage of times it came up heads. So this, we're seeing that there were 9 tails and 1 head. So let's run that one more time. Now it's 50%. So every time you run it, there's going to be a huge difference between the results you're going to get. Now we'll go up, run this 10,000 times. Now it's really close to 50. And if I run it again, it's again close to 50. So the larger the number, the closer it's going to be to what you would expect, or the actual probability, like we talked about last week, of your distribution. So what that means is going to be chosen 50% of the time. It's not going to be close to 50% if you run it 10 times, but 10,000 times, every time it's going to be close to that 50% mark. So that is exactly what I'm about to demonstrate with the central limit theorem when we're talking about it.
So in this case, the sample of 10 is not a good choice.
No.
Now the sample of 10,000, going back to this question.
Yes.
How to choose a sample. So better pick 10,000 because it gives realistic answers.
Yeah, and there are very specifics to that rule that I'm about to cover. And then I'm going to explain that, because so there's specific numbers that you need to sample in order to get it to look correct. So I'm going to talk about that now. So at the end, I'm looking at all the percentage of all. So I ran it 10 times and then returned the percentage of each individual time I ran it. So then I aggregated the results at the end. So this is the central limit theorem. This is the basis of pretty much everything you're going to do in statistics. It's extremely important. So what I'm saying, what I was explaining about the random sampling earlier, this is why that works. So the central limit theorem says, and this is a little odd, but I'm going to explain and show you what it means in a minute. So if we repeatedly pull a sample from a population, we'll have to repeat the multiple samples from that population. Say we have a population of 10,000 people, and we pull 30 people from it randomly. If we do that, say 100 times, we pull those 30 people. That's kind of what it's talking about here. So if you have random sampling, say 1,000 times, we pull 30 people. That's not intuitive. So I'm going to try to explain that in a different way, and we're going to see it, because that's one of the things that I'm like, oh, how do I explain that? Okay, so an example. We have, we're sampling all the people in Texas about their opinions of the power companies. So if we have, do we have a lot of brownouts? Do we lose power a lot? Is it too expensive? That kind of thing. So we, in order to do that, want to sample, say 5,000 people. And if you sample those 5,000 people more than once, so I'm sampling 5,000, and then I come over here and sample 5,000 again, and sample 5,000 again. That's what that's talking about here. So say we do that, where we have 30,000 people and we sample 1,000 people 100 times. What the central limit theorem says, when we take the mean of those individual samples, they are going to be normally distributed, which I'm going to explain in a second. So we would need to sample a lot of people a lot of times, find the mean of each sample, it's going to be normally distributed.